So we have physics Ph.D. qualifying exam practice problem number 8 in classical mechanics. So let's begin. A particle moves in a uniformly rotating frame with the given angular velocity. Omega vector equals omega z hat. This being omega scalar, z hat. So the effective potential is given as such that phi sub EFF r comma z equals negative gm over square root of r squared plus z squared minus 1/2 omega squared r squared. Parts A through H. Part A, derive the equations of motion in the rotating frame. Part B, identify the centrifugal force. Identify the Coriolis force. Part C. For Part D, determine the equilibrium points. For Part E, linearize the equations around an equilibrium point. Part F, construct the stability matrix. Part G, determine the stability criterion. And Part H, discuss connections with the restricted three-body problem and the stability of the Lagrange points. Okay, so let's begin here with Part A. Okay, so Part A here. Equations of motion problem. For a unit mass particle in the rotating frame, that Rw dot sub ROT equals this entire expression here. Okay, these bold omegas are vectors, bold capital omegas, and R double dot equals the following. All out to that cross R dot sub ROT. Okay, and because we have these centrifugal term is contained in phi sub EFF. So our equations of motion, we're going to use rotating Cartesian coordinates x, y, z, with r squared as x squared plus y squared. And r equals the square root of x squared plus y squared plus z squared. So we're going to have that phi sub EFF equals negative gm over capital R minus 1/2 omega squared times the quantity x squared plus y squared. So the rotating frame equations are going to be here, here, and here, three parts. That x double dot minus 2 omega y dot equals negative partial of that phi sub EFF with respect to x. And y double prime plus 2 omega x dot equals negative partial derivative phi sub EFF with respect to y, and z double dot equals the negative partial derivative phi sub EFF with respect to z. With the following, this partial derivative of phi e sub ff with respect to x equals this: gmx over r cubed minus omega squared x. And we also have that partial derivative of phi sub EFF with respect to y equals gmy over r cubed minus omega squared y. And then here, partial derivative of phi sub EFF with respect to z equals gmz over r cubed. So our explicit equations are going to be as follows. X double dot minus 2 omega y dot equals negative gmx over r cubed plus omega squared x. Y double dot plus 2 omega x dot equals negative gmy over r cubed plus omega squared y. And z double dot equals negative gmz over r cubed. Okay, now for part B, they want us to identify the centrifugal force. So here, let me just adjust this. Okay. So the centrifugal acceleration is negative omega vector crossed with the cross product of omega vector cross that r. Vector equals scalar omega squared r hat, or in Cartesian form, that a sub cent equals omega squared x hat plus omega squared y hat. And this comes from the potential term negative 1/2 omega squared r squared. For part C, they want us to identify the Coriolis force. So the Coriolis force, the Coriolis acceleration is A sub COR equals negative 2 omega vector times, cross product. I should say the cross product of negative 2 omega vector and R sub ROT dot. And with this omega vector equals scalar omega z hat, and R sub ROT dot equals the following: x dot y dot z dot. Our A sub COR equals 2 omega scalar y dot x hat minus 2 omega scalar x dot y hat. And this is the reason for the equations containing negative 2 omega y dot and 2 omega x dot. Okay, so that's for letter C. Now moving along to letter D, they want us to determine the equilibrium points. So let me just get this out of the way. So letter D, equilibrium points. Equilibrium in the rotating frame requires R dot equals 0, R double dot equals 0, and then we have del phi sub EFF equals 0. Sorry about that, that's a del. So gmx over r cubed minus omega squared x equals 0. Gmy over r cubed minus omega squared y equals 0. And gmz over r cubed equals 0. The third equation gives z equals 0. And for a non-zero radial position, r cannot equal 0. The first two equations imply that gm over r cubed equals omega squared. Therefore, r naught equals this quotient gm, and so this gm over omega squared, that quantity raised to the 1/3, and z naught equals 0. And because the potential is axisymmetric, every point on the circle, x naught squared plus y naught squared equals r naught squared, or z naught equals 0, is an equilibrium point in the rotating frame. For part E, they want us to linearize the equations around an equilibrium point. So here for part E, linearization about an equilibrium point. Okay, so choose one equilibrium point, for example, x naught, y naught, z naught, and we'll set that equal to r naught, comma 0, comma 0. We're going to write the small perturbations as x equals r naught plus xi, y equals eta, and then z equals zeta. So what we have here also, we have the Hessian. I blocked that off, not sure why. The Hessian of that that phi sub EFF at this point is phi sub XX equals negative 3 omega squared, phi sub YY equals 0, and phi sub ZZ equals omega squared. And with mixed derivatives is 0. And we could finalize just as finalization here. The linearized equations are as follows here. So we have this xi double dot minus 2 theta eta dot equals 3 omega squared xi, eta double dot plus 2 omega xi dot equals 0. And here we have zeta double dot equals negative omega zeta. And the z motion is a simple harmonic oscillator. And my apologies, this was accidental. This should not be in bold. So just again, this right here, this zeta should not be in bold. Okay, and for part F, construct the stability matrix. So the stability matrix here for part F. Okay, so stability matrix, we're going to let U equal the following. There's 1, 2, 3, 4, 5, 6 terms in this column. So it's going to go from here, xi, eta, zeta. That's xi dot, sorry about that, eta dot, zeta dot. So right there in that fourth spot, that's xi dot. Sorry about that. Then U dot equals AU, and where A equals the following matrix. So here's our A matrix, 6 by 6. Okay. So that's letter F. Letter G, they want us to determine the stability criterion. So let's see here for letter G. Okay, so for letter G here, stability criterion, look for solutions proportional to e to the lambda t. For vertical motion, lambda squared plus omega squared is 0, so lambda equals plus or minus I omega. So the vertical motion is stable, oscillatory motion. For the planar motion, lambda squared, xi minus 2 omega lambda eta equals 3 omega squared xi. And we're going to wind up with also omega squared eta plus 2 omega lambda eta equals 0. Now the characteristic equation, that comes out to lambda squared times the quantity lambda squared plus omega squared equals 0. That's from constructing this determinant, constructing this and then taking the determinant. So solving that, lambda equals 0, 0 plus or minus I omega. And the non-zero eigenvalues are imaginary, giving oscillatory behavior. The double zero eigenvalue reflects the continuous circle of equilibria and the freedom to shift along the circular orbit. Therefore, the equilibrium is neutrally stable, but not asymptotically stable. A small displacement produces bounded epicyclic type oscillations, plus possible drift along the equilibrium circle. And moving on to the last one, letter H, discuss the connections with the restricted three-body problem and the stability of the Lagrange points. So here for letter H, connection to the restricted three-body problem and Lagrange points. This is mathematically similar to the circular restricted three-body problem because both are studied in a uniformly rotating frame and use an effective potential, whereas this xi sub EFF equals xi sub GRAV minus 1/2 omega squared R squared. And that's the gravitational potential there for that. Phi sub GRAV. So in the restricted three-body problem, the Lagrange points are equilibrium points satisfying this del phi sub EFF equals 0. Here, instead of 5 oscillated Lagrange points, the symmetry of the single central mass gives a continuous ring of equilibrium points, whereas we have R equals R naught equals this quotient of GM and omega squared that raised to the 1/3 Z is equal to 0. The linear stability analysis is also analogous. One expands around an equilibrium point, includes the Coriolis terms, forms the stability matrix, and studies the eigenvalues. And we could say that the rotating frame equilibrium circle is neutrally stable. Okay, so thank you for watching, and have a great day.